Question 2 from activity 4.2. And you probably did it on Friday, which was the 9th. Yes? Did you put a date with it? Always put a date with it? Alright. So it says there, find a word in B that fits with the word in A. Just write down the symbol. Alright. The first one there, 2.1, they say sound. Let's start, Genevieve, with you. What fits with sound? Yes, it is B. It says it needs a medium to propagate. 2.2, Carabello, the speed of sound. Each is higher in a denser medium. 2.6, 2.3, Karabu, ultrasound. Okay, it's obviously not B. So your ultrasound, your choices is it has a frequency greater than 20,000, or it's an echo, or it is directly proportional to the pitch. Yes, it is A. Okay, so A is gone. 2.4. Lesego. A reflection of sound is C, it's an echo, yes. And 2.5, Telefu, frequency of sound, it is D, same as pitch. Good. Back to your notes. Okay, we were speaking about echoes. And where are we? Tell me anything you remember regarding echoes. Anything you remember regarding echoes? It's a reflection of sound, yes. More, Amora? Good, they reflect better off hard surfaces than soft surfaces. More, Asina? Are they transverse waves or longitudinal waves? Longitudinal waves? Why? Are they longitudinal waves? What waves are examples of longitudinal waves? Yes, but I'm going to give you 3 options. Light waves, water waves, or sound waves? Sound waves. Alright, so you guys remember a few things. So we spoke there about ultrasound and how you see the picture of a baby. And then another use of sound waves or echoes is when in industry, and we mean there like in a mechanical industry with machines and stuff like that. Ultrasound is used to clean machine parts. So what they do is they send out ultrasounds and then it shakes the machines. It's the same frequency as machines. The machines shake and then the dust particles falls off, or they examine welding, so they see is there a gap in the metal, so they reflect it, and if it goes too fast, or if it goes a bit slower, they know, there's a air gap because it travels slower through air, right? And so forth and so forth. All right, let's look at a question. It says there, when the depth of the Titanic was determined by using sonar, the time elapsed between the transmitting and receiving back of the wave, the echo, was 4.4 seconds. If the speed of sound in seawater is 1480 meters per second, calculate the depth of the Titanic. Atlean, what is the Titanic? You don't know? Anyone? Yes, Amara? No. Omelimu? And what happened to the boat? It sank. It was a big, there's a movie on it. It came out in, I think, 1994, actually. A big boat that sank. A real life story, and a lot of people died. And the reason why it's such a big thing is because the people that made the boat said, "Not even God can sink the boat." And then he did just that. How do you pronounce my name? Do you know? Charlotte. Charlotte. Right, so the Titanic, that's obviously now the movie, but Titanic was a massive, 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 massive boat, and then it hit an iceberg. That's the movie. Yeah, I don't think they have a picture of how they thought it hit the iceberg, but it hit the iceberg and then the Titanic started to go down and then it broke in half there and the whole thing collapsed. Alright, so then it went down to the bottom of the sea, and there you can see a few pictures of it at the bottom of the sea. Alright, so they say the Titanic, there's a boat, oopsie, trying to locate the Titanic. Here is the Titanic. Obviously that's the picture of a boat for me. On the bottom of the seafloor, yes? Yes, a few. Mostly children and women that they put on small lifeboats, but not a lot. Alright, so what happened here is they say using a sonar they sent out waves. And are you drawing the picture? Because I know what's happening. And then the waves were received back, the echo. Okay, info table. They speak there about 4.4 seconds. Okay, tabeleng. 4.4 seconds. What information do they give us there? Oh, good, yes, seconds is in period, but what else is in seconds? Time. Okay, they give us time. Then they speak there about 1,480 meters per second. Genevieve, what do they give us there? Yes, the speed. And then they ask calculate the depth. Carabello, what are they asking us to calculate? But what is the symbol of depth? What do you measure depth in? If I ask you, how deep do you think the Fall River is? What would you say? Okay, so you measure depth in meters. What else do you measure in meters? Niemand, take out a unit. Go to the previous page. Hello. No, the distance. So they are asking you the depth, how deep, the distance between the boat and where the Titanic is lying. Okay, but Karabu, in here, we have a bit of a problem. Because that time is the time that it took for the wavelengths to be sent out and to be received back. And they only want the depth. What are we going to do? What? We're going to divide by 2. Because that time, that 4.4 is all the way to the bottom and back. And we don't want it all the way and back. We just want it, how deep is it? Okay. So whenever they speak about an echo, you know you must divide the time by 2. Okay. So you go to your data sheet, and remember this formula is actually not on your data sheet. You fill in the values exactly where on the correct places it should be, and then you rearrange. Sejo? We're waiting for you to do the calculation. It's not your first day in my class. Yes. Sejo? 3,256. Yes. And the unit again? Meters. For those that are struggling, you want x on its own, and it's at the top, you want it there. So you want to get rid of the 2.2. What do? You take it to the other side and you multiply it. Talefo, 3,256 meters. How many kilometers is that? Sorry? I can't hear a word. Am I supposed to? In 2 kilometers. .256 kilometers. Divide by 1,000. Alright. Then we are going to go to pitch and volume. Okay, it says there, the volume of sound, so here we are busy with the volume. The volume of sound is linked to the amplitude of the vibrations. So the bigger the amplitude, the bigger the volume. Okay, now before I read any further, take out a ruler. Let's see. Right, Now, the first one I want you to draw is just one wave, a normal wave like that. Now, with that information, Sizwe, the volume is linked to the amplitude. How will a wave look that has a softer sound? How smaller? Smaller like this, smaller like this. Yes. So this there is the amplitude. So a softer sound, you're still going to draw one wave. It's still going to be the same distance from there to there, more or less. But now it's going to have a smaller amplitude. Yes? Because why what I'm saying now is probably in this day and age. But anyway, why are you considered to be black? Say again? Like how? Because you have darker skin, right? Okay, now some people nowadays identify as blah 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 blah, but we're not going to go into that. So you consider black because you have darker skin. Same thing here, because it has a softer sound. When you have an oscilloscope, you know I spoke about oscilloscope that give you that wave. When that wave comes onto the oscilloscope, it is like that. It's just smaller. That's just how it is. Does it make sense what I'm saying? So there's not like someone decided, okay, with a calculation, now we're going to draw it smaller. That's how it is. Right. Amora, so if something has a louder sound, what will the wave look like? Yes, it will be high up. So again, I want you to draw one wave, not two waves. Again, I want it to be more or less the same length. Okay, so not shorter, not bigger, same length. The only difference now is it's going to have a bigger amplitude. Right, so I'm going to go back here. It says there, the greater the amplitude, the higher the volume, the louder the sound. Okay, and then it says loudness is a relative term because our ears have different sensitivities. Some people have very good ears, so when they speak, or when you speak, it's very loud to their ears, and some people have weak hearing, so you can speak very loud and for them it's still soft. Okay, so it just says loudness is actually a subjective term because it's for everyone is different. Yes. No, they have. There's so many parts. There can be a lot of different things that do not function as it should. All right. Then the next thing we're going to look at is pitch. Okay, and pitch is linked to the frequency of the vibration. Okay, so pitch has to do with how low or how high you speak. So it has nothing to do with how good your voice sounds when you sing. There's nothing to do with how loud, how soft you speak. It has to do with your pitch. So some people, maybe some teachers, maybe me, when we speak after a while, you just like, you can't hear to that, you can't listen to that pitch anymore. Have you felt that way? Or if we think about Mr. Kutzer that sang this morning, he has a very low voice. Yes? This pitch is very low. So pitch has to do with the how do you say it? Your depth with which you sing. You sing with a very high voice or a very low voice. There's nothing to do with loudness. Okay, so now none of you sing choir. So you have sang before. So if you sing choir, then when you go for audition, you get a certain voice that you sing. So you can either sing soprano, that's very, very high, or you can sing alto. Alto is for girls, quite low, and then for men, it's a vast, it's very, very, very low. Alright, so that has to do with pitch. Okay, so how will pitch differ or look when we draw waves? Again, we're going to draw a wave there. Now remember, I can ask you to draw these waves in a test or an exam. So we're not just doing this to color in your notes. Okay, so again, let's draw a normal pitch. But for now, a normal pitch, I want you to draw 2 waves. Don't make it too difficult for yourself. Okay, 2 waves. When something has, can I highlight here? It says here at the second bullet, an increase in frequency results in an increase in pitch. So it means they are directly proportional to one another. If the one increases, the other one increases. But Asina, what is frequency again? How do we calculate frequency? Say again there. You are right. I just want it to be loud. What does the hashtag stand for again? Yes, the number of waves over the time, the total time. So frequency is how many waves. Here we drew 2 waves. So if something has a lower pitch, Omulemu, how will we draw it then? Yeah. Bigger, how? Okay, in the width, yes. So, normal pitch, let's say this is a certain time frame. Let's say that is 1 second. Okay, so here we have 2 waves in 1 second. Again, we have 1 second, but now we must have, with a lower pitch, we must have less waves. So now we're going to draw 1 wave. Okay, same amplitude, more or less, same amplitude, because we're not making it louder or softer. We're just having less waves. What's fout? Then why are you frowning? Don't think you're going to figure out later. You must ask now. Go ask the grade 11s if there's something like we will figure it out at home by ourselves. You don't. You never do. Yes. Because frequency is how many waves in a certain time. This is 1 second. Here we have 2 waves. So the frequency will be 2 over 1, 2 hertz. This first one. This one has a lower pitch, meaning it must have a lower frequency. So again, in 1 second, because these blocks are the same size, in 1 second we have 1 wave. So it will be 1 over 1, it will be 1 hertz. This was 2 hertz. This is going to be 1 hertz. So because it has a lower frequency, it will have a lower pitch. Sharp. So, we did answer. Atleham, a higher pitch. What will you see in the same time frame? Say again? 3 waves or more waves. Right? We didn't say it's 3 hertz, but yes, more waves. So here we're going to draw 1, 2, 3. So, well, I forgot about this. Okay. Next thing is we've spoken about in and out of phase, and we spoke about a bit about standing waves in the video. Now, a lot of the times I do not have all the apparatus for all the experiments, the practicals and stuff that I want to do. So then I go to this online website. It's called Phsc Simulations, from a university in America that have these practicals that you can do online, and it's for free. So you can go play with it at home, and it has a lot of different topics. So you can see there are simulations at the top. Then it says physics, chemistry, maths, earth science. Earth science is like geography, and biology is life sciences. Okay, so if you want to see if there's a practical in another subject that you're curious, you can go look there. We are busy with physics, and there's two things that I want to show you. Okay. Right. So here we have this is like a water tank. These are two taps that you can drop water in, and you'll see it make these ripples, ripple effects. Okay. On the right hand side, you can see there I can change the frequency. So frequency is, let me just start. Frequency is how often does it drop water. So you can see if I increase the frequency, it's going to drop it more often. And if I lower the frequency, it's going to take longer for it to drop. Okay. Then another thing that I can change. I'm going to up the frequency a bit. Another thing that I'm going to change there is the amplitude. The amplitude, you can see it changed the size of the drop. Size of the drop there is small, and if I make the amplitude bigger, then the drop becomes bigger. Then I can change the separation of the two taps, like that. Alright, so what I want you to see is you can see there's this blue and the dark ones. The blue parts are where the two waves, the two crests of the wave meet each other, and we call that again constructive interference, where they build each other up so it makes a bigger crest. Where the smaller the black lines is where there's destructive interference, where there's an up and a down and they cancel each other out. Do you remember that? Okay. You can also see these two water droplets are in phase, so they make dots at the same time. Okay, so you can see there the waves that it makes. I quickly want to stop this one. Did it stop now? Yes. Okay. Can you see the amplitude of the wave is now smaller? And as soon as we have two droplets, then there's constructive interference, which means they build each other up. So now they form a bigger wave. Alright. We can also do the same with sound. Okay, so there you can music playing, you're at the Valentine's dance, and yeah, yes, right, so there you can see music playing, and again you can see constructive and destructive interference and an interference pattern. And then the same, just quickly want to show you here. Okay, so here it shows you the wave. Here it shows you the particles. Remember we said sound waves are particles that collide. So there you can see just the bouncing over particles back and forth. Okay, let's say we look at that ball there. Back, look, So the waves don't go on and on the particles. The particles just vibrate like this, back and forth, back and forth, back and forth. Right. Then here I have a laser. You all know what a laser is, right? So you can see there, it makes a nice green pattern. because the frequency is on green. Now this is the next part that we're going to speak about. We have different light. We have red, yellow, green, blue, purple, whatever. Red waves, I'm going to change that frequency on the right hand side. I'm going to change it to red. Now red waves, what I want you to see, has a bigger wavelength. So you'll see the red part, the color part of red, it's going to be bigger. Can you see it's a bit bigger? Small difference. And then if we look at purple, it's going to be a lot smaller. Right, that has to do with the wavelength of different light. Different light have different wavelengths and different energies. And we're going to speak about that in the next lesson. Alright. Then the next thing I want to speak about is okay, so here you can see we have like there's a loose end, the wave can just go on, and here I can move the wave like that. Now I do not make a nice wave, so I'm going to let it oscillate. So oscillates go up and down by itself. Right, so here we have a transverse wave. You can see there I can change the amplitude here at the bottom, make it bigger, make it smaller. I can change the frequency. Frequency means how many waves, how fast does it move. High frequency, lower frequency, less waves in a certain time frame. Then damping. There, can you see that it loses some of its energy? Okay, so I just want to change that to very little. And tension is just how far the particles can move from each other. Is it high tension, then the particles are close together. Low tension, the particles are far away from each other. Alright, so what I want you to see now, I'm just going to change the frequency a bit down. Okay, and amplitude as well. Okay, so now I want you to see, this is now open-ended, meaning the wave can go on and on forever and a day. Now we're adding a loose end then. Okay, so you can see the same. There we go. The wave goes. Let me just make this a bit smaller. and restart. Okay. So what you can see there, it goes up and down, and because of that loose end, yes, there's a bit of a reflection, but it's not a constant reflection going up and down, because the wave can almost, the energy can be released a bit. Okay? But what I want you to see is if there's a fixed end, then you can immediately see, let me up the frequency and restart. Then you can immediately see the reflection in the wave. Can you see that? Okay, and as soon as you see that, I'm just going to make this a bit bigger. Okay, you can see the wave almost up and down, I want to say, up and down starts to form a pattern. Wow, wat wil ek doen? Like that. Restart. Okay. You can see the reflection, and you can see they start to build on each other. Right. So, what I want you to see is it almost looks like the wave, I want to say, stays where it is. This one goes up and down and up and down and up and down. Can you see that? That we call a standing wave. A standing wave. Because it just keeps on going up, down, up, down, up, down. Even though there's waves coming in and waves going out reflection, it looks like the wave is just staying where it is the whole time. That is called a standing wave. Alright. So with all of that in mind, on this page, this is the in and out of the phase that we spoke about and the interference patterns that we saw. Okay, so in phase is 2 points that are separated by a whole number multiples of a complete wavelength, and out of phase is that are not separated by whole number multiples of a complete wave. But this we have already done on the second page. So it's not new news. What is interference patterns? It's when two sets of waves formed on the surface of a wave by two sources that are in phase. I'm going through this quickly because, like I said, we have done it. Okay, so you need to be able to point out where we have constructive interference, where we have destructive interference, out of phase, in phase, blah, blah, blah. And you need to tell me this is called an interference pattern. So I can show you a picture like this and ask you, what is this called? Then you're going to tell me this is called an interference pattern caused by points that are in phase and out of phase. Right. Then standing waves, like I just said, the up and the down and the up and the down and the up and the down. Standing waves are produced in a string when successive pulses. No, are we with you? Yes, we are with you. What does successive mean again? Successive pulses. No, how can I explain this? Were you here with our previous deputy principal? Do you know who that is? Mr. Malan. Now, Miss Daniel is his successor. Do you know who's Miss Daniel? So, what is successive? Call a friend, ask the audience 50-50. Who are you calling? Sizwe, incoming call. Yeah, he's using your lifelines. Successor, 50-50. Is it when things happen at the same time or when things happen one after the other? One after the other. Okay, so successive pulses means, so we get standing waves when you have pulses one after the other. So it's produced by pulses one after the other. Now, doubling, you didn't know what the word successive mean. Did you write down? One after the other. When successive pulses move through a string attached at a fixed point at one end. So we have that fixed point. Okay, this is the result of interference between incident pulses and reflected pulses. Genevieve, what is incident pulses? Incident pulses and reflective pulses. Karabu? No, constructive interference will happen when this pulse and this pulse meet. Incident pulses is incoming pulses. So they're pulses being produced. So the pulse is going this way, is incident pulses. And then reflective pulses is the ones that are reflected. Okay, so when these two pulses meet and they meet the same speed through a common medium, through the same medium, then you get interference. And this standing waves play an important role in sound production and quality of musical instruments. So I told you that pitch, on the previous page, pitch has nothing to do with how well you sing. Pitch has to do with how high or how low you speak. You speak very high, you speak very low. But standing waves, a type of standing wave that you produce when you sing, that has to do with the quality of your voice. Like some people can sing very well, and some people are not that gifted in that. I still can't believe I made you guys sing. And I still can't believe you did it. You sang. Okay. Alright. Okay, what's what you say? Okay, so here you can see the standing waves. So I just say here, pitch and loudness are two different things, and they have to do with the type of wave fronts, and the wave fronts, the waves that are produced, is different in every musical instrument. Like the waves that are produced in a flute and a guitar and a piano all are different because the musical instrument is different. Okay, so they sound different. Even though they can play the same note, they sound a bit different. Alright, so here you can see is a standing wave. Here you can see is one wave, or half a wave actually. This is one wave and these are 1.5 waves. Right, now in here you must know two things. You must know here B is called the antinode. The antinode. The antinode. That is the maximum amplitude where you get constructive interference. Okay, so the way you should read these standing waves is one wave at a time, meaning you look at that. Because this wave there is like the reverse wave. You know, we saw that doop, 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 doop. So this is like the reflection wave that you see the next second. So that there is where you have constructive interference because two waves have already produced a higher amplitude. So it's not like this wave and this wave is going to meet and have deconstructive interference. No, no, no. That wave there is coming later. That wave already experienced constructive interference and have a higher amplitude. So it's the antinode, and then here A is called the node. That is where they've already experienced destructive interference, but there's no movement. Sorry? Yes, exactly. Exactly. All right. Now we're going to go to the next type of wave. Now the next type of waves, I actually want to show you a video. Okay, so let's see if we can.
20%. Connected to Charlotte's like
Why did you choose Nestle Namkid?
Nifika is such a brilliant child, so we needed the right premium drink to support.
Nestle Namkid is the obvious choice.